Myself Dr. M. Ayyappan, Assistant Professor, Department of Electrical and Electronics Engineering, NPR College of Engineering and Technology, NATHAM. Today we are going to discuss about the topic for reactance diagram sample problems. So, the first problem is a 300 MVA 20 kV 3-phase generator has a subtransient reactance of 20%. The generator supplies two synchronous motor through a 64 km transmission line having transformer at both ends as shown in figure. In this, T1 is a 3-phase transformer and transformer 2 is made up of 3 single phase transformer of rating 100 MVA. So, 127 bar 13.2 kV 10% reactance, series reactance of the transmission line is 0.5 ohm per kilometer. Draw the reactance diagram with all the reactance marked in per unit. Select the generator rating as base value. So, in this problem the one generator is present and the two motor is present as well as transformer 1 and transformer 2 is present. The middle of the transformer 1 and 2 transmission line is present. So, in this case, so the base value, that means is considered as a new base value, that means generator base value is same as a new base value as well as new KVA or new MVA. Okay. So, in this problem 3-phase generator having 300 MVA and 20 kV, the reactance of 20%. At the same time the transmission line length is 64 km. So, both ends of the transformer is 64 kilometers long, that means 64 into reactance. And next one, the two transformer value is transformer 1 and transformer 2 is different. Transformer 1 is a 3-phase transformer and transformer 2 is made up of 3 single phase transformer. So, that is the difference. And the same value, the reactance value is 127 bar 13.2 kV 10% reactance. So, finally using all those values, finally we can draw the reactance diagram. So, this is the sample network. Actually, in this case generator is present 300 MVA 20 kV and 20% reactance. So, and transformer 1 is present and transformer 2 is present. Transformer 1 is 3-phase transformer. So, 20 bar 230 kV and 350 MVA 10%. So, but transformer 2 is 3 single phase transformer. So, multiply the KVA value into 3. So, 3 into 100 equal to 300 KVA and 300 MVA, reactance of 10%. So, and the transmission line is reactance for 0.5 ohm per kilometer. So, the transmission line length is 64 kilometer long and the motor 1 and the motor 2 is connected in the last that means end of the power system network. So, in this motor 1 200 MVA 13.2 kV 20% reactance and motor 2 is 100 MVA 13.2 kV and 20% reactance. So, in this case section 1 and section 2 and section 3 is calculated. So, the section 1 is for the generator side and the section 2 is middle of the transformer 1 and transformer 2 is considered as a section 2 and in between the motor 1 and motor 2 to the transformer 2 is considered as a section 3. First we can calculate the individual section of the HT and LT rating of the value and afterwards each and every individual per unit, that means new impedance value is calculated in the next section. So, first calculate the value for section 1. Section 1 is KVB new equal to 20 KVA. In this section actually the new base value is considered as a same generator value. In this case KVA value is 20 kV. So, for section 1 KVB is new value is also 20 kVA and for section 2 is from the relation KVB on HT side of T1 equal to voltage rating on HT divided by voltage rating on HT. into kVb on LT side of T1. So, voltage rating on HT divided by LT. So, voltage rating on HT divided by LT, that means actually in this section 230 divided by 20. So, please see the transformer 1 values 20 bar 230, 350 MVA and 10%. So, same as like that HT divided by LT means 230 divided by 20 into kVb on LC side of transformer 1. Already calculated the value for section 1, kVb new value is 20 kVA. So, the same value is written on the HT side of T1. So, kVb on LT side of T1 value is 20. So, 230 divided by 20 into 20 equal to 230 kVA. So, kVb on HT side of T1 is 230 kV, and for section 3 from the relation kVb on LT side of T2 equal to voltage rating on HT divided by voltage rating on HT into kVb on HT side of T2. So, actually in the transformer 2 13.2 divided by 220. So, the please see the value for transformer 2 value, that means kVA value 220 divided by 13.2 kV. So, LT divided by HT means 13.2 divided by 220 into already the section 2 value, that means transformer 1 value is written on the value same as to the T2. So, kVb on HT side of T2 value is from the section 2 value into 230. So, 13.2 divided by 220 into 230 equal to 13.8 kV. So, in this case section 1, section 2 and section 3 is calculated. Next we go for the generator side. Individual per unit impedance value is calculated. So, section 1 is 20 kV and section 2 is 230 kV and section 3 is 13.8 kV. For the first generator side, you will calculate the new impedance value. So, XPU new equal to XPU old into kVb old divided by kVb new to the whole square into MVAB new divided by MVAB old. So, this is the formula for calculating the impedance value of, that means new reactance value of generator. So, per unit value of that means reactance value is J 0.2 and kVb old value is 20 and kVb new value is also 20 divided by 20. So, do not confuse with that 20 divided by 20, old value is 20, actually the new base value is also same as generator value. So, 20 divided by 20 whole square into MVAB new value is 300 and MVAB old value is 300. So, finally, we get the results XPU new equal to J 0.2 per unit. Next we can calculate for transformer 1 side. So, the same formula XPU new equal to XPU old into kVb old divided by kVb new whole square into MVAB new divided by MVAB old. So, the transformer 1 reactance value is J 0.1 and kVb old value is 20 and kVb new value is also 20 into MVAB new divided by MVAB old 300 divided by 350, that means new value divided by old value for MVA, kVb old divided by kVb new 20 divided by 20 whole square. So, finally, we can get the results for transformer 1 into the new impedance value of XPU new equal to J 0.0857 per unit. The unit is per unit. So, next we can calculate for transmission line. So, actually this is a very important one. So, in this case reactance of the transmission line is 0.5 ohm per kilometer. So, actually in this diagram middle of the T1 and T2 your transmission line reactance value is 0.5 ohm per kilometer. So, already given in the problem the transmission line kilometer length is 64 kilometer. So, the total reactance of the transmission equal to J 0.5 into 64, that means reactance of the transmission line into total kilometer of the reactance, that means 0.5 into 64. Finally, we can get the results for J 32 ohm, that is the actual value of transmission line. Next we can calculate ZB. So, what is the reason for calculating the ZB? That means base impedance value means actually after calculating the new value of reactance equal to X actual divided by Z base, but in this case actual value is directly is given in the same problem J32. Okay, already calculated value for transmission line is equal to J32 is calculated, but base value is not given. So, directly I am going to calculate the base value. So, ZB equal to KVB whole square divided by MBAB. What is the value for KVB? 230 whole square divided by 300. So, Z base value equal to 176.33 ohm. So, this is the Z base value. So, directly substitute the value in the XPU new. So, X actual divided by Z base equal to J32 divided by 176.33 ohm equal to J 0.1815 per unit. So, this is the value for per unit value of the reactance in the transmission line. So, next we can calculate for transformer 2, same formula XPU new equal to XPU old into KVB old divided by KVB new whole square into MBAB new divided by MBAB old. So, actually the XPU old value is J 0.1, KVB old value is 220 and KVB new value is 230, MBAB new value is 300 and MBAB old value is 300. So, directly substitute all those values in the same formula. Finally, we can get the results for J 0.0915 per unit. Next, we can calculate for motor 1 and motor 2. So, the two different synchronous motors are connected in the same network. So, first we can calculate motor 1. So, XPU new equal to J 0.2. So, this is all those values are just you can consider in the individual motor value. Okay, each and every time we can calculate at the different components like motor and generator, transformer 1, transformer 2 and transmission line. In this case only each and every time you can focus on that your individual value of the various components in the KVA value and MVA value as well as reactance value. So, in this case XPU old into KVB old divided by KVB new whole square into MBAB new divided by MBAB old. So, the value for XPU old is J 0.2 and KVB old value is 13.2, KVB new value is 13.8 and MBAB new value is 300 and MBAB old value is 200. So, just to substitute all those values in the same formula, directly we can get the results for J 0.2745 per unit. So, this is the value for motor 1. Next we can calculate it motor 2. Reactance value is J 0.2, KVB old value is 13.2 and KVB new value is 13.8, MBAB new value is 300 and MBAB old value is 100. So, just to substitute all those values in the same formula, finally we can get the results for XPU new equal to J 0.5489. So, this is the reactance diagram. So, after all the values are calculated, directly we can draw the reactance diagram. So, EG is nothing but generator, XT1 is nothing but transformer of reactance, XT2 is reactance of transformer 2, XTL is reactance of transmission line and EM1 and EM2 is motor 1 and motor 2. Okay. Actually, based on that given power system, sample power system network, we can draw the reactance diagram. First generator is present. So, in this case EG J 0.2 per unit and afterwards of generator is directly connected with transformer 1. So, your generator is directly connected with T1 and the value is J 0.857 per unit. After connecting the transformer 1, directly will connect the transmission line the J 0.1815 per unit and afterwards transformer 2 is connected, the value is J 0.0915 per unit. So, after transformer 2, two different synchronous motors are connected, machine 1 and machine 2, that means motor 1 and motor 2. The motor 1 value is J 0.2745 per unit and the motor 2 value is J 0.5489 per unit. So, I will summarize the overall problems. First, we can calculate the individual section of the power system, individual section of the HT values and LT values on the same network. Afterwards, we can calculate the individual components value, that means individual power system components value, that means generator value is calculated, transformer 1 is calculated, transmission line is calculated, transformer 2 is calculated and then motor 1 and motor 2 is calculated. So, afterwards we can draw the reactance diagram. Just in this reactance diagram we can just mention the calculated values in the reactance diagram. So, this is the procedure for drawing the reactance diagram in the power system network. Thank you.